Welcome back, guys, to part 3 of this series. In this video, we're going to be tackling the communication from our main controller to our device, which uses Modbus RTU over RS485. And as a recap, these are all the devices that we're going to need to make this happen. Now, our main controller doesn't have an RS485 module on it already, so we'll have to convert TTL to RS485 with a separate converter module. And then, since we don't actually have a real device, we'll be simulating it with a Modbus server on our PC, which is why there's an RS485 to USB converter here. Now, just as a reminder, this is the layer structure we'll be using. And in this video, we're just going to be creating another service to communicate with the device like we did in the last one. Now, let's figure out what we need to know before we actually start writing code. First, I want to figure out how we're going to go from the microcontroller to the RS485 converter. We know that the converter module is TTL, or serial, to RS485. That means we're going to want to utilize a UART on our controller. So let's go into our controller reference manual and find which one we'll use, because I'm sure there's a few. Here it's showing me that my controller has these UARTs. 1 through 3 are USARTs, and I've never even used one of these before, so I'm just going to stick with the basics here and utilize UART 4. If I go into my board's user manual, I can see that the port C pin 10 is UART 4's transmission pin, and port C pin 11 is UART 4's receive pin. So I'll be hooking these up to the converter module's data in and out pins. Okay, so we got one piece of the puzzle done. Now we need to understand how to hook up to our converter module. So we have two sides to this thing, a TTL/UART side and an RS485 side. Let's start with the TTL side. On the left side here, we have the DI pin, which stands for data input. This is where the transmission, or the TX, of our UART, also called PC10 pin, will connect to. Then we have RO, which stands for receive output. This is where the RX of the UART, also known as PC11, will connect to. Next is the RE and the DE pins, receiver and driver enable. We're actually going to tie these two pins together and connect them to one of our GPIO pins on the controller. This is because when the single GPIO pin is high, that will enable the RS485 driver to transmit data and disable reception. And when the GPIO is low, that will disable transmission and enable receiving. So it's pretty nice that we can control the flow with only a single GPIO. On the right hand side, the RS485 side, we have VCC, which will hook up to the 5-volt pin on our controller. A and B, these are the data lines. They're a differential pair. The A is going to hook up to the A on our USB to RS485 converter, as well as B to B. And ground will just connect to the ground on the USB device as well. Here's a wiring diagram. You can pause if you need to. Cool. Now we know how we're physically going to get data from our device, but we also need to know what data we're going to get. If this was a real device, there would be a list of Modbus registers provided by the manufacturer. In our case, we're just going to make some up. So let's talk about what we're going to use to mimic our device first. I'm using a program called Modbus Slave. You can go to that website and download the appropriate version, and it's good for 30 days before they make you purchase a license. When you open Modbus Slave, you'll be greeted by some empty registers. So we'll just fill in a few: voltage, current, and temperature. And we'll give them some arbitrary values as well. Okay, let's just make it a little bit more clear what we're doing here in case you've never worked with one of these before. We have a simulated device, and on that device we have a Modbus server, which in our case is the Modbus Slave program. Then we have our microcontroller, which is the client. The client sends requests to the server, and the server responds accordingly. In our case, we will be requesting the voltage, current, and temperature values being stored on the server. Okay, now I think we can start coding. We're going to follow the same procedure as last video. We'll create our service directory, populate it with the appropriate files, add it to our top-level CMake file, enable anything that we need to in our proj.conf file, and then of course get to writing the service. We are going to be doing a couple new things here with CMake, but I'll go over that later. So we've created our main files. Let's go ahead and populate our CMake file. We can just go into the TSS service and copy and paste what's in there and change it accordingly. And don't forget, the next directory up, we need to make sure it points to this new directory that we've created. Otherwise, the top-level CMake file will get to the main services directory and not be able to find its way to the new BDS service. Since we're going to be utilizing UART4 with the Modbus protocol, we need to go in and make it known in the device tree. So let's go ahead and do that now. Let's talk about what we've done here. Now we've nested Modbus 0 inside UART4, which is stating Modbus communication will occur over UART4, and that Zephyr's Modbus driver will use UART4 as its transport layer. This line here, DE GPIOs, is equal to, yet we defined the driver enable pin for RS485. If you remember back to the RS485 diagrams, we tied the RE and the DE pins together. Our microcontroller is going to use GPIO port D pin 4 to drive those high and low and control the flow. Let's not forget to enable things in proj.conf. So we're using the Modbus protocol, so we need to enable Modbus. We're using a UART, so we need to enable serial communication. And we need to enable interrupt-driven UART communication. This just prevents our UART from stalling the thread until data is received. Our loop can do other things in between transmissions. Let's go into our BDS source file and start filling that out. Let's get in all our includes. Let's register our service with logging. When we get the Modbus interface from the device tree, we'll use a function that returns back the index of the Modbus interface, or a negative value if it failed to find it. So we'll need a variable to store that in. Next, we'll create our Modbus parameters interface. For mode, we'll use a define already created in the Modbus driver for us. That's for RTU mode. For the receiving data timeout, we'll create a define up above. Now, for whatever reason, I have to set mine to 70,000, which I believe is milliseconds. That doesn't make any sense to me that I have to set mine for a timeout of 70 seconds, because that's insane. If I set it any lower, I start getting weird issues when reading data from the Modbus server. So there could be some sort of mismatch or some weird thing I got going on with the server. But if one of you knows what the issue may be, please leave a comment telling me why. Then for baud rate, we'll create another define and set it equal to 19200. Pretty standard baud rate in Modbus. For parity, I'm going to create a define and set it equal to UART config parity none. And then for stop bits, I'll create another define and set it equal to UART config stop bits 2. We need a single do-it-all function that can read holding registers from our Modbus server that other global functions we create in this file with more specific duties can utilize. I'm going to call this function BDS read holding registers. And with Modbus, when you read holding registers, you've got three main items you're dealing with: a starting address, the number of registers that you want to read, and then where you're storing the data associated with that register. So this function will have those parameters. This function is going to wrap another function called Modbus read holding regs, which comes from Zephyr's Modbus driver. We need to pass in two more arguments in addition to the three parameters above. First one is our Modbus client interface variable that we created above. The Modbus server ID, which is going to be just 1. I'll create a define for that up above. And then our starting address, the variable that will hold the data contained within the register, and then the number of registers. And to make it more clear on how we're getting the data, when we call BDS read holding registers, we're passing in a pointer variable for the register data. The wrapped function, Modbus read holding regs, that just returns a 0 to us if it was successful. Let's create an initialization function. So far, all I want to do in it is get the Modbus interface from the device tree. This is where we'll set the MBus client iFace variable using a function called Modbus iFace get by name. And we'll reference the Modbus 0 name that we used in the device tree earlier. Then we'll initialize the Modbus client with that interface value, as well as the Modbus parameter struct. Before we can retrieve data from a specific Modbus register, we need a way to keep track of and look up registers efficiently. To do this, we'll use a JSON object to store the register mappings. In this JSON object, each key will be a descriptive string representing what the register is for, like voltage, current, temperature. And each value will be the corresponding Modbus register number. With this structure in place, we can create a function that takes a register name as input, looks up the corresponding register number from the JSON object, and then retrieves the associated Modbus data. However, I don't want to have to parse a JSON object every time I want to find a Modbus register. So instead, I'm just going to have a Python script that converts the JSON object into a C struct and then places that new struct into a generated C include file that my BDS service source file can include and utilize the new struct. Here's a horrible sequence diagram to describe the process visually. You, the programmer, starts the build process. CMake calls the Python script. The Python script opens the JSON file and then generates the new include file with the C struct, which contains all the key value pairs from the JSON file. This way, if I ever want to add, remove, or change any Modbus registers, all I have to do is edit the JSON file. Then rebuild the project, and the build process takes care of everything for me. Let's figure out where to store the JSON file and then make the JSON object. Since this is a sort of configuration, if you will, and it's only related to our BDS service, I'm going to create a folder called config within the BDS service directory. Then I'll create a file called bdsregisters.json, and in this file I'll make the JSON object with the correct key value pairs, referencing the Modbus server that we looked at earlier. Then I need a place to store the Python script. I'm going to create a directory called scripts and put it there, and then create a Python file called json2c.py. Now, since it's been a long time since I've written anything in Python, I'm just going to have ChatGPT generate me a script that opens the JSON file and converts the object into a C struct. It took me about 7 or 8 tries going back and forth with ChatGPT to give me something that was actually usable. But I'm assuming if you've been programming for any amount of time, you've probably learned how to make decent prompts. So I'll skip that part. But I'll copy and paste the script into here, and you guys are welcome to pause and copy it if you like. But I want you to pay attention to these decorators here, the click commands. These essentially allow CMake to pass in any JSON input file and any output file to the script. Just makes it more dynamic. Now let's go into our top level CMake file. We did forget to add our new BDS service to it, so let's do that real quick. Let's integrate the Python script. I'm going to use the set command to create a variable that's equal to the path to the Python file. Then I'm going to create another variable that's equal to the path to the JSON file. And then I'm going to create another variable that's equal to the path of where I want the output file to end up. We need to tell CMake to generate a file with these variables. We do so by using the command add custom command. Output and then the output inc file variable here tells CMake which file will be generated. Command is stating what command will be run. We have a variable here, Python executable. We didn't define this, and there is a CMake command to define which Python executable to use, but it is working for me, which means it was automatically defined somewhere already. So if you do have problems, you may need to define that. Then we have the name of the Python file, and then our arguments to the script, which is the JSON file and then the output file paths. So this portion here is the equivalent to this if you're going to run a Python script from your command line. The depends just states what the command depends on. So if either of these files change, the command will be rerun. We need to add one more thing here for this to work. We need to use our output include file variable in the target sources command. This is so CMake knows that this file should be included in the compilation process. If we didn't do this, you wouldn't see the file appear in the location we designated for it. I'm going to try building the project now. Looks like I have an error in my device tree, probably when I added the Modbus interface inside UART 4. Yeah, looks like I was missing a space here. Let's try to build again. I have some warnings here. I'm going to ignore those for now. Okay, I haven't written anything in the BDS service header file, which means the general includes file never got included, which means my BDS service has no idea what the term global even means. So let's fill that out real quick. Okay, we got a successful build. You can see the script generated the include file with a couple arrays. The main one I'm going to be concerned about is the key value pairs one. So yeah, that's awesome. Let's go into our BDS service source file and include this in there. I want a function now that will read multiple Modbus registers at a time and get the data stored within them. Let's create a function for that. This function takes in an array of strings, which will be the register keys we want to look up, an array of uint 16s to hold the data contained within those registers the keys relate to, an array of integers for the request results, which will tell us if we successfully queried that register from the server or not, and then the quantity of keys that we want to look up. This outer for loop will loop through each of the passed in key strings. We only do something if the key isn't null. Otherwise, we set the result for that key to be a failure. Then, in this inner for loop, we will loop through all the keys in our generated key value pair array and compare them to our passed in key strings. If they are a match, we send out a Modbus read request to get the data and place it in the registered data array. If we never find a match for the current passed in key, that means we pass in a key that doesn't exist in our generated array. I need to add these global functions to the services header file so they can be accessed in main, and we can test this out to see if we can successfully read data from our Modbus server. Let's include this in main and get some test code going. Okay, let's build this to see if everything is good. Got an error here. I didn't include the generated file from the config directory, so I'll fix that. And it looks like I didn't reference the results variable correctly in a couple spots. Should be results, not result. Okay, we got a successful build again. Now let's go into our Modbus server and get that running. Go up to connection and then connect. Make sure all your settings match what your Modbus parameter struct says that we set up in the BDS service. So that's going to be 19200 baud rate, 8 data bits, no parity, and 2 stop bits. Press OK after that. Now let's flash the program to the board and see if we can read from the server. Okay, so far so good. I don't see any bad logs and the data is matching. So let's go ahead and change the data on the server. Okay, looks like it's tracking. Sick. So that will conclude the video. Next time, we'll start building out the CAN bus application. See you guys next time.